Okay, so let's talk more about finding limits without actually looking at a graph. So we have a list of rules for limits, and it all starts with if the limit of one function as x approaches a is L, the limit of another function as x approaches a is M, then all of this stuff is going to be true. It's saying that if we're adding two functions together and taking the limit of that sum, we can split that into the sum of two limits. In other words, add together L and M. Same thing for a difference, same thing for a product, same thing for a quotient. All of these four are going to be similar. And then C, rule C says if we're taking a constant times a function and taking the limit of that, we can just take the limit of the function and then multiply by the constant. Similarly, with exponents, if we're taking the limit of something cubed or squared, we can take the limit of the function, then square that value. And really, G is redundant since roots are exponents, but the one thing to note is that this is only true if the limit is greater than 0 when n is even, because if n is even, L is negative, we have imaginary solutions. So let's take a look at some of this. We want to find the limit of x plus 3 over x squared plus 1. First thing, is x equals 1 a value where this function is undefined, where it's discontinuous? No, it's not. So that's good. What we can do is let's use these limit laws. Limit x approaches 1 of x plus 3 over the limit x approaches 1 of x squared plus 1. Now another limit law. Limit x approaches 1 of x plus limit x approaches 1 of 3 All right, there's one more limit law that we can use. And that's the one for an exponent. And what is the limit of the function y equals x as x approaches 1? Well, it's 1. And the limit of 3 as x approaches 1, well, 3 doesn't care what x is doing. 3 is always 3. Limit as x approaches 1 of x is 1 squared plus 1 in the denominator, and we get 2. Now, you might say, well, Mr. Schnack, that's great, but why couldn't I have just plugged 1 in there and done a direct substitution and got right down here? And the answer is you absolutely can. The thing you have to be careful of is making sure that the function is defined for that value, because if it's not, then a direct substitution is not going to work. It's going to give you problems. Second example, find the limit as x goes to infinity this time. Well, we can't plug infinity in because infinity is a number. However, if we look at this intuitively, we get really big number plus 3 plus really big number plus 1. So we have really big number over really big number. This is what we call indeterminate form. Indeterminate form when we have infinity over infinity, but unfortunately that tells us nothing. So we have a strategy for this, and I think I've mentioned it in one of my other videos, but we're going to divide all of the terms by the highest power of x, and in this function, that highest power is x squared. Now to simplify, 1 over x plus 3 over x squared, 1 plus 1 over x squared. Now, we can take the limit of each one of these independently, much the same as we did over here, and we know that the limit of something over x is going to be 0. So in the numerator we have 0 plus 0 over 1 plus 0. Our limit as x approaches infinity is 0. How about this one? Now, notice if we do a direct substitution, we end up with 0 in the denominator. And we can't divide by 0. So that's not helpful to us at all. So let's try some algebraic manipulation. If we're going to evaluate this limit, if it's going to exist, we need this x plus 4 to go bye-bye. We need it to divide out. We need it to cancel, if you will. And the numerator is factorable. So just quick question, what do we have at x equals negative 4? A hole in the graph. So this is equivalent to taking the limit as x goes to negative 4 of x minus 1, and that we can do direct substitution with. Our limit is equal to negative 5. This is kind of like that question where it was, we had that funny thing here and then k there, and this was when x doesn't equal negative 4, when x does equal negative 4, and the question was, what does k have to be so that this whole thing is continuous? Well, it would have to be negative 5 in this case. And that was from one of the earlier videos that I did in this section. All right, so last thing to talk about is geometric series again. Well, we've talked about that, right? Okay, but let's frame it in the idea of limits, and I may have mentioned this when we looked at the sum of an infinite geometric series. So this geometric series will converge, it will have a sum, when the absolute value of r is less than 1, because the sum from 0 to infinity of a geometric, we could think of that as being the limit as n goes to infinity of our geometric sum formula. And we know that the limit as n goes to infinity of r to the n is 0 when r is a fraction, when the absolute value of r is less than 1. These terms will get smaller and smaller and smaller and smaller. So taking the limit of this becomes u1 times 1 minus 0 over 1 minus r, giving us this sum formula. So my question for you today is, does this converge? We could start to evaluate this. We get 2 plus 3 halves plus and if you're looking at these terms, you're going, no, that is not geometric. There is no common ratio. That does not converge. But that's actually not correct, guys. We can think of this in a slightly different light. What if we split this into 2 separate fractions? Isn't that the same thing? And the rules for summations are actually identical to the rules for limits. So we can split this into 2 separate sums. And these are both infinite geometric series. First one has a first term of 1 and a common ratio of 5/6. Second one has a first term of 1 and a common ratio of 2/3. So this sum becomes 6 plus 3, or 9, ladies and gentlemen. And that is where I shall leave you today. In the next section, we start finding about this thing called a derivative and seeing how awesome it really is.